Okay, so let's get started. Today, what we are going to do, we are going to discuss about earthquake prediction system. Okay, in earthquake prediction system, we have taken a problem from Kaggle.com, which is known as LANL earthquake project. So, on first, I am going to explain you what LANL project is, the basic specifications about what was the input available, how they have generated earthquake, the virtual earthquake in the laboratory, and then how they have generated the data and how you can use that data to perform earthquake prediction analysis for a laboratory kind of environment. To do that, you can quickly reach out to Kaggle LANL earthquake prediction. You can quickly search for it. Once you reach out to LANL earthquake prediction, over this page, you're going to get complete information about what the competition was. So this competition was started by a laboratory from US. They have, with that virtual lab setup, they have generated certain data for different machine earthquake can be identified. So to quick forecasting earthquakes, okay, and will occur, where it will occur, and how. This is the problem statement which has been taken center. Okay, so now the challenge is hosted by Los Alamos National Lab, from which the data has been set up. Section here, and under additional screen you can quickly observe, and I will annotate that with a graph. The actual observe, there are three important things here. There are sand particles available. Okay, whenever they are, so by generating a signal, this slide will change, and due to this rock pieces, and due to that earthquake kind of. In order to get to know more about this, an artificial setup of a data set was generated. Now let's quickly get back here. So I hope you have got this information. Second part is environment it was. Let me just quickly share with you. There is an article known as article, and within this shaking earth article, what has been generated. So earthquake environment in the lab has been set up. I'd like to show you some quick glimpse out of it. So here you can see that this is a virtual lab setup which has a lot of electronics and signal machines available within the lab itself. There's a pool of hardware. Then there are central pieces. There is this generator here using which the signal will be passed, and there are certain rock stones would be available. When the signal will be generated, earthquake will be formed. So I'll take you a little further in this video just to give you a quick idea about what exactly they were trying to do with the lab itself. So now here you all can quickly see. So what you guys can do is you can quickly go through with this video. I'm going to share the link of this video in the chat section so you can observe. So here you can quickly observe what they were trying to do. They have taken some random stones. These are, let's say, the left slide and the right slide. And when the left slide is tuned towards up or is moved towards upside, and the second slide is moved towards the second side, so there is a signal generated at the epicenter, and due to this, earthquake reaches to a lot of region. Let's say it reaches out to the world at different places. So now what we have to do is consider we are at this location. Okay, this is our house, and let's say the epicenter of earthquake will be here. A signal will be generated here. So we have to predict in how much time the earthquake will reach out to the people or to the country or to whatever location we want to quickly identify. So currently we are trying to identify at India location, let's say, that how, in what time the earthquake is going to happen, depending on the signal initiated. So this is this is the information which we have got here. Now let's quickly proceed to the next part of this, that how the code has been implemented. So there are two things which we need to understand in the data, and I'm going to quickly explain you. Now what we have done is, under your earthquake prediction, I have maintained a cloud server. There are two things which we need to do. The application has been hosted on a cloud server, which is an Amazon EC2 instance. And I have prepared this Amazon EC2 instance over here. Let me quickly show you. It is at console.aws.amazon.com. So when you reach out to AWS Amazon console, I have already shared a PPK file with you in case if you would like to show the backend code of the instance. I have made an instance here known as Earthquake, and the IP address of this server instance is this 13.232.16.187. So you can note this IP address. This is the server IP address where we are going to set up our source codes, from where this application will run and the model will be deployed. In order to access this, you need to have a PPK file, and this PPK file has been uploaded here. So in your card here, Data Science Intern 3, I have uploaded the PEM file here. Here is the PEM file using which you can quickly connect to AWS server using PuTTY, and you already know the IP address of the server. So, but still I give you the IP address. That's EC2-user at this IP address. Sorry, I'll quickly get back the IP address. That is okay. So this is the username, and you need to convert this PEM file into a PPK file. So for that, I think you have already done. You already understand how to convert PEM into PPK. In case if you don't know, I'm going to share an AWS video with you where we have taught how to convert PEM file into a PPK file, and then how to use that PPK file to connect to the server. So you can quickly access your Amazon instance. In order to quickly access the Amazon instance, we need to use an SSH command, or you can use PuTTY in order to quickly connect that. But I'm going to discuss the code side part first. So over that EC2 server, I have deployed this train.csv, which is of 9 GB. So the actual size of this data set is 8.9 GB, which has been deployed over there. So for analysis purpose, we have imported all the libraries. The major important libraries used here is pandas in order to create the data frame and maintain the data. Then the data will be converted into NumPy arrays of 1 dimensions and 2 dimensions to perform standard scaling. So that's why we have used NumPy in order to convert our 1-dimensional data into 2-dimensional data sets. And this is required when we perform standard scaling part. So we have also used standard scaler from pre-processing libraries. We have used this because we have to represent the data between 0 to 1. Let's say we want to transform the data of different sizes between a value of 0 to 1, and we will be transforming data using standard scaler function. Then we have used a grid search CV in order to quickly create the cross validation matrix from the training set available, and we can perform analysis over it. Now over that, we have used kernel ridge algorithm. Kernel ridge algorithm gives you better accuracy in prediction of the response time or the time to earthquake. So these are the libraries which have been imported. This is the data which has been imported. Now post the data, what we have done, we have quickly checked how many rows and columns we have. So the data contains approximately these number of rows for different signal values and the time left for earthquake. Similarly, it has 2 columns. The 2 columns in the data includes, I'm going to quickly show you. So by default, the data set which was available, it has 1 column known as acoustic data and time to failure in the original data set. But we have renamed this information from acoustic data to initial shake data, which means the signal at the epicenter, and the second value is changed to time left for earthquake, which means the column will be denoted as the time left in seconds before the earthquake happens. Now here we have displayed top 5 values from the data which we have got, approximately 8.9 GB. We have only displayed top 5 values here. So here it shows you have an initial signal value and you have the time left for earthquake. So generally, depending on the data which was originally generated by the laboratory, we have got this information over here. Now post that, what we have done. So we have got to know about data that we have two variables. These variables has to be converted into dependent and independent variable. So dependent variable will be known as time left for earthquake, because we are going to predict time left for earthquake, and the independent variable will be our initial shake. We are going to call it as independent variable. Now the benefit of independent variable is that using this independent variable you can predict the outcome, you can predict the dependent variable value. Okay, but here you can see there is a very big problem, and the problem is that we only have one independent variable. Okay, and it may be possible that this variable may not be much or directly relevant to the dependent variable, or it may be possible it could not be able to predict individually the value of dependent variable. So for this, what we need to do, we need to generate more independent variables. So now what the objective is, since one variable, I'll just type here, since one independent variable is not sufficient to predict, time left for earthquake, we have to generate more independent variables. Okay, so in order to generate more independent variables, we have written a function over here, and this function is known as generate features function. Okay, now once you have got this information, let us just quickly view that what exactly we have done under generate features. So under generate features, what we have done, we have taken the value of initial shake and we have calculated the arithmetic mean, the standard deviation, the minimum value, the kurtosis value, the skew value, and the quantile value out of out of the out of the original independent variable available to us. So now, as you all can already understand what mean is, you also understand what is standard deviation. You also understand about mean, minimum value. Here, I'll just get over here. Similarly, you understand about kurtosis value, skew, and quantile. Quantile, I'm going to give you a quick look. It can compute the kth quantile of the data along the specified axis. Okay, so similarly, we are generating certain 6 features in order to have some more data which can easily predict time to earthquake. So now we have generated this function, generate features. In the next cell, what we have done, we have read that 8.9 GB file. Depending on that 8.9 GB file, we have created a data frame for training data, because we will be having a 2-dimensional data with n number of columns. So now we need a data frame, because here we need two-dimensional data with 6 columns. And what are these 6 columns? These 6 columns will contain the value of mean, standard deviation, minimum, kurtosis, skew, and quantile. These values will be taken over here. Now, once we're done with that, we are going to read all the values available in the training data. We are going to generate the features, and we are going to append the values in the XTrain. So the values of initial shake will be stored into XTrain, and there will be 6 values generated for every X value. And these 6 values I'm going to show you in the graph below. Similarly, you're going to read time left for earthquake, and you're going to store that value under Y train. So this is how we are going to write this code. Followed by, I have shown you the value of X train which we have got. So X train is our independent variables. And now you can see we have got 6 independent variables here. So these 6 independent variables would be difficult to understand with the numbers. So in the next cell, what we have done, we have changed the index to the specific names. So we have converted the name to mean, deviation, minimum, kurtosis, skew, and quantile. So 0 will be represented with mean, 1 will be represented with deviation. So this means out of the initial shake value which was available to you by default, you have generated 6 more values so that you can perform analysis well, and you have some independent variables to predict the dependent variable. So this is how your independent variables will now look. So this is your data which will be taken for analysis. Okay. Now here, when we have taken this data for analysis, it is always recommended to represent the value between 0 and 1. So all the columns will be distributed, transformed into a value of 0 to 1 using the formula of standard scaling, which means x minus x mean upon mu, which means, so you can quickly check the standard scaling method. We have already discussed about standard scaling in our machine learning class. So once you have used the standard scaling function, we have got these values are now converted between a value of 0 and 1. Okay. So now once we have converted it into a standard scalar, now what we have to do, we have to perform using the algorithm. So here we have taken some parameters, the gamma parameters and alpha parameters, which are required for kernel ridge class. So kernel ridge is the algorithm. Kernel ridge algorithm combines ridge regression with the kernel trick. You can read more about kernel ridge regression algorithm uh, from the references. Now here, using the kernel ridge, we have taken certain features like kernel features, the parameter features, and we have selected this algorithm and we have created a model out of this. So a model has been initialized. Now we have calculated the values of the model by providing him X train values, which means the training data, and the dependent variable which you want to predict from the training data. So this training data has been provided to model, and once the model has been fitted, we have used model.predict function to predict the value of different time left for earthquake depending on the input signal values. So now here you can see that you have got the output of time for earthquake for different input values of signals available in the data set. Now, in order to verify whether the model is good or accurate, we have plotted a graph here. To plot the graph, we have used plt.figure, f.add subplot, and now we have got the plot here in which you can see that this plot is plotted between actual earthquake versus predicted earthquake. Okay. On the x-axis, you have time left for earthquake, which I'm going to define here. This time left for earthquake is in seconds. And here on the left-hand side, we have the initial signal at epicenter. So epicenter you can consider is the center from where the earthquake generated. And these are certain values of initial signals which were available in the training data. Now, depending on this information, we got to see that we have got a graph which is somewhere pretty near to the actual cases. As you all can see here, all these cases are approximately very close. Only a few cases are not matching when the value of signal is very high. So at that point of time, it is somewhere difficult to identify time for earthquake. So sometimes it is possible that we couldn't get the appropriate value. But in most of the cases, you can see that we have got a pretty close value of the predictions. Okay. So now we can consider that the algorithm kernel ridge is a good algorithm in order to predict the earthquake for this time series data, for the acoustic data. Now, so once we are ready with the model, now what we have to do, we have to export this model for web integration. To export this model for web integration, we have created a quick file. Now in this quick file, we have named this file as earthquake web model. Within this, we have initialized all the libraries. We have the function generate features, followed by we have here we have started the process of final exporting of the web model. So in order to finally export the web model, we have used system arguments to receive the values, and we have stored it into an input signal. This value we are going to receive from a web application. Okay. So we are going to receive a value from the web application. We are going to give it as a signal. Then we are going to create a data frame for the initial shake value, and whatever input we are going to take from the user interface from the web application, we are going to save it into input signal, and a blank data frame will be created with the value which we have received. Followed by we are going to call generate feature, so that from that input value we can generate features like mean, minimum, and all the relevant 6 features which we need to have in the input data. So we are going to save that into xtrain. Now we have to perform pre-processing on xtrain. So there are certain not available values. So to replace not available values, we have used fill NA. Now, depending on that, we have converted that into NumPy arrays. So initially, once we have created this, we have got a series, and we have converted this series into a NumPy array here. Now, once we have converted this, we have converted this into a 2-dimensional array here. Okay. So here, when we have converted series to 1-dimensional array, and in the next step, we have converted 1D to 2-dimensional arrays. Okay. So once we have converted that into a 2-dimensional array, we have got the xtrain values, which we have taken from the real-time input, which we have got from the web application. Followed by, we have performed standard scaling for data transformation. And finally, what we have done, we have loaded the model. Okay. So what is this model loaded? I'll quickly take you to the previous script. The model which we have made here, we can export the model simply using this 3 line of code. You can import pickle. You can give name of your model file which you want to include or integrate with a web application. This can be your PKL file which has to be integrated with the web application. And finally, you are going to call this function pickle.dump. You're going to take your model. This is the model, the algorithm which we have taken here. This is the model algorithm which we have taken, grid search CB with kernel rich. Now, using this model, what we have done, we have got pickle.dump. We have open a file name with write privileges, and now the earthquake model.pkl file has been exported on the local system. So I'll show you on Jupyter Notebook. Once we have executed that, we have got an export model here. I have already downloaded that model, so I'll quickly show you how the model looks like. So you're going to get an earthquake model.pkl file downloaded. Now what you can do is, once you are integrating it with the web, you have to call this function pickle.load, and you have to open earthquake model.pkl with the read privileges, and you have to store that into a variable known as loaded_model. Now, once the model has been loaded, we are going to call a predict function, loaded model.predict, and we are going to provide the input values which we have received from the web interface and which has been transformed with the scaling and transformation function. And finally, we are going to get a result. So once we are going to get a result, you can quickly see that, let's say I have given a sample value 5. So I'm going to convert that sample value into a 2-dimensional array. And depending on that, we are going to get a result array. And from the result index, we are going to get a value returned, which is going to be the time in seconds which is left. This is the time which is predicted depending on the input data provided. Now, once we have got this information, we can export this model. So what you can quickly do is you can go to file, you can download this file as a PY file. Once you download this file as a PY file, this file has been downloaded here. I have uploaded the file here. Okay, so here you're going to get all the files. So this is the PKL file which has been exported. This is webmodel.py file which has been uploaded. Just give me a moment. Okay, now here. So similarly, this model is going to be exported and we have got this model here. Model.pkl you already have. This is the earthquake web model.python file, which you have to integrate it with the server side. Now you need to upload these files over the server. In order to upload the files over the server, you need to have wget command. I have written the sample command over here. I'll just show you again. Now what we need to do, once we have uploaded this, now we have to create a website. To create a website, we have made a project here known as the earthquake project. So within this earthquake project, we have an index.html file. And here in the index.html file, we have designed the user interface somewhat like this. Okay. So I'll just take you here. Under the index.html code, if you click here, earthquake prediction system, we have created this value here in kind of a div tag. You need to know a little about HTML in order to do that. Followed by, we have got a video control. So we have created a video control here under the section. Under the section, we have this list element, which represents your video. And within this video, we have got a YouTube video, which we have connected here. We are going to automatically play this video once the earthquake occurs, just to give a feel that, okay, some earthquake is really happening, just to give an impression that earthquake is happening. Now, post that, we have got a value known as earthquake prediction system, which is written over here. H1, this control has an ID known as countdown, and the countdown value will be represented over here. So we have written the code in jQuery there, and I'm going to explain where that code is. Similarly, we have got a trigger button. So we have created an A tag, and using that A tag, we have used the ID trigger. So as soon as somebody is going to click on trigger, a trigger value will automatically be generated for up to a second. So let's say if you are pressing the trigger signal for 3 seconds, so a value 3 will be generated. If you are pressing the trigger signal for 10 seconds, let's say, so a signal value of 10 will be generated, and automatically that value will be sent to the prediction model. Prediction model is going to receive the signal. It is going to perform generation of features. Then it is going to perform data transformation. It is going to predict using the model. And finally, the output value is going to be returned, and we are going to get the seconds for earthquake. Okay. Now, similarly, once you have got this information, at the very bottom, we have specified this information for the team. The team name has been specified over here. Now, how all this logic is working from the front end, for that we have got a script here on line number 175. On line number 175, we have got the script which is doing all the logical part. So what we are doing, as soon as our web page gets ready, okay, we are going to initialize two variables, start and the stop variable. Similarly, we have taken the video resource information so that later we can modify the video source and we can play the video. Similarly, you're going to have a trigger function here. Now, what the trigger function is going to do, we have set up two automatic trigger here. Let's say if somebody is going to perform mouse down, what we are going to do, we are going to grab the start. We are going to get the time. This is going to be known as the start time. We have also tested a vibration feature, but somehow on various devices vibration doesn't work. It's totally a device based feature. So there are some mobile phones in which if somebody is going to press the trigger signal from epicenter, he's going to feel the mobile phone vibration as well, just to give a glimpse of the earthquake epicenter signal. But in mostly in computer devices and in general mobile devices, the feature doesn't work by default. You can also test this feature with with Mozilla Firefox. Various devices with Mozilla Firefox features have this feature of experiencing the vibration also on the mobile phone. Okay, so mouse down feature is for web applications, for websites where a real mouse is used, and pointer down trigger is used on the mobile phones. So once somebody is going to perform a touch event, then pointer down is used. And in case if somebody is using a laptop or a machine and he is using a mouse, so then mouse down function is used. So to give the compatibility for both the mobile phone and the website for the desktop applications, so we have used both these functions. Now what we are going to do, we are going to get the time and we are going to define the countdown value signal from the epicenter. Now, as soon as we are done with that, we are going to get the stop time as soon as the mouse up is done. As soon as a person removes his mouse clicking from the button, the stop time will be calculated. Now we are going to parse the time. This is generally available in milliseconds. So we are going to convert these milliseconds into seconds by dividing with 1000. Then we are going to perform a console log just to identify the start and the stop values, what has been taken and what is the time left. This is a console based information just to check the values going, transferring between client and server, just to check what values are going and what response is coming in. Similarly, once we have got the values, the time left value, what we are going to do, we are going to display epicenter signal value here. That what is the signal value transmitted from the client side to the server side. Okay. So the initial signal which we have to generate, and depending on the initial signal, machine learning processing will be done and we are going to get an output. Now, once we have got this value, we are going to send a post request to a file known as predict.php. We are going to send a signal value to this predict.php, and finally the predict.php is going to respond us the value of time to second. So what this predict.php is doing, we have written a pretty simple code here for predict.php, wherein we are receiving a signal information from our client side, and then we are sending this signal value to our earthquake web model.py, which is hosted on the same location on the server side. So we are going to send a request user anaconda bin python 3. Using python 3, we are going to ignore some warnings, which general warnings which comes from Jupyter. We are going to disable them. Then we are going to call earthquake web model.py, and we are going to concatenate the value of signal. And finally, whatever output we are going to generate from this earthquake web model.py, they will be returned back and it will be printed back to the server. So this is predict.php file which we have taken. I'm going to explain earthquake web model.py. I have already explained it, but again, I'm going to show you where is it in the server side so that you get a better idea. So going back to index.html, once the request has been sent, the request will go to predict.php. Predict.php is going to send it to earthquake web model.py file along with the signal value, and we will wait for the response. As soon as the response comes from the predict.php file, we are going to log the response. We are going to set the interval function, and we are going to get the value, and we are going to split the value from dot. We are splitting the value from dot because from in the original output, I have already shown you that the output which we are going to get will be in this format. So this is something like 4.7 seconds, which is 4 seconds, 7 milliseconds, let's say. So we are going to split the value from point. Okay. Now, depending on that, we are going to get the seconds value out of it. And then we have written a basic function to calculate the value second by second, just to give a quick look that a timer is running and the time to earthquake is reaching back. Now here what we are going to do, Then again, we are going to update this countdown prediction system value. And here we are going to show a timer that how many seconds left for the earthquake. As soon as that happens, we are going to get a message known as earthquake, and our video will start running, which will show a real image of how an earthquake happens or something like that. Okay. So this is how we have written this function. Similarly, we have the pointer up function. This is the same function which we have used for mouse up, but this function will work on a mobile phone. So similarly, once we are done with that, we are going to have a click on the video resource and the video is going to play. So this is your web application model which has been designed. So it has been coded in HTML and jQuery under the index.html file. Along with that, we have used PHP in order to receive the values and send it to the web model. And now on the server side, we have a web model.python file, which I'm going to show you. So this is the earthquake web model.py file, which I have already shown you, which has the generate features. And this is the code of receiving the value at the server side. You're going to receive the input value from predict.php. Then you're going to perform the data pre-processing part, wherein you are going to fill the zero values. You're going to convert from one dimensional to two dimensional. Then you're going to perform data transformation to standardize the data. Once the data is standardized, you're going to load your model, which you have generated from your original analysis. And this was the original analysis which we have done. And after performing analysis, after receiving this graph, we have exported the model using this way. Okay. So once we have got the model loaded, we are going to predict using the generated model. Okay. So where is this code available? I can quickly show you. This code is available here on the server side. So in order to quickly connect the server, for Windows users, if you are using Windows, you need to use PuTTY. If you're a Mac user, you can directly connect with SSH. Okay. So since I'm using Mac, I'm going to connect with SSH, but you guys can quickly use PuTTY, and I can share a video with you where you can use the PM file to convert into PPK using PuTTY gen, and then you can use that PPK file using putty.exe to connect to the server by providing your IP address and the username, which is already available under your Trello card. Now here, we are going to quickly go to downloads. Under my downloads, I have devanshu.pem file. And here we are going to connect with ec2-user at, and we are going to define the IP address. So once we are going to connect it, it is going to ask you the password, and we will log into our server console panel. So now here on the server side, I have a Kali Linux based server, and this Kali Linux server has a World Wide Web directory. So here we have started Apache server, and the Apache server's directory is var World Wide Web HTML, where all our code is available. So once we open this file here, you can quickly see we have uploaded index.html and our CSS and assets which were available to design the website. Similarly, we have uploaded predict.php, we have uploaded earthquake model.pkl file, and we have uploaded this earthquake web model.py file. Okay. So let me show you earthquake web model.py. You can use Nano editor to use earthquake web model.py file to quickly see the code. So this is the Jupyter code which we have generated from Collaboratory. Here we have imported Pickle and other important libraries. Then we have called this function generate features, followed by we have collected the input signal. In the input, you can see we are receiving the parameters from command line argument, and this value will be coming to us from predict.php code. So using the system command at predict.php, the signal value we have received from the post request will be given to this Python file. And followed by that, we are going to generate a data frame. We are going to perform data pre-processing. Then we are going to perform data transformation using standardization. We are going to load pickle.load. And finally, we are going to perform prediction using model, and we are going to get the result back. Okay. So you can also test this file manually also. So what you can do is you can use this command user anaconda bin python 3, and you can quickly run this on an earthquake python 3, and run that on this model earthquake web model.py, and you can give any value of the signal. Let's say I would like to give a signal value as 8 seconds, or I would like to give a signal value of 2 seconds. Similarly, we can do different values and we can quickly check back. So once we are going to execute that, you can see that we have got certain warnings, but we want to suppress the warnings, and this is the final output 4.7. So what am I going to do? Let's say in order to suppress the warnings, we have used this command -w warnings ignored. So once you execute this, now this time you're going to get the output in seconds. This output in seconds will be received as a response in the jQuery, and then the timer will be calculated and it will be displayed on the web page. Now here, what next you need to do? Let's say you're going to use any different value. Let's say I'm going to use a value of 15, or there are various other things we need to quickly check back, depending on what kind of values are being given, depending on the model and depending on the data. So you can quickly take up different values and you can check back what values are coming in. Okay. So now let's just quickly clear that. So here is how we have uploaded the model on the server, and just to quickly give you the information, here is the train.csv which we have used for data analysis, and we have also uploaded all these codes in a zip file over here, using which you can access that. So all your web application code is coming from here. And similarly, we have now, once we have uploaded that code, let's quickly go for testing of this, that how we quickly test that. So in order to do this, what we generally do, you can quickly browse your application now on 13.232.16.187. Now this web application page which is displayed to you, this comes from the index.html file which we have generated. Now in order to quickly see the demonstration, what we can do is we can go on inspect. Okay. So under the inspect, you can quickly change the view of your inspect from here. Now under this inspect, we have to go to the network tab and the console tab. You can quickly clear this. This can be very helpful for understanding what is happening with the process. So let's say for testing purpose, when I click on trigger signal from epicenter, I'm going to keep it clicked for some time. Let's say I'm holding it. As soon as I release it, so I'm going to get a epicenter signal value. The epicenter signal value was 5 seconds, so 5 was displayed. We have got that value loaded. Okay, just let me just quickly refresh it once. Okay, so let's say I'm going to send again a value of request. I've got a signal value of 1, so I'm going to get a return value. I've got 4 seconds now, 5 4 3 2 1, and I've got that. So this is how the code runs, and we get the value of the response value, and it gets displayed over that server. Okay. So if you have any queries, now you can ask me. Okay, if you have any queries, please ask me. Okay, clear. Okay, fine. So now what is happening here? All your codes are available over here. I'll just quickly give you a look here. So earthquake model is on that. You have to use PM to access the cloud. There you are going to get all the files. here is your earthquake web model.py, which is available for prediction at AWS server side. Followed by one more thing. This is the website code. Okay. So what I can do is I can give you an updated website. I think this is the updated website code which I have uploaded over here. Once I'll do what I'll do is let me just give you another one which could be like a pretty more updated one. And this will be here. Okay, so let's say this is going to be the earthquake website.zip, and let me quickly upload at your Trello cards. Okay, this earthquake website code you can open in brackets IDE. That will be easy for you. You can quickly extract the zip file and all the specific codes are available over there. Here, I have uploaded it. Okay, so you have got the analysis code, you have got the web integration code, you have the website code, you have the AWS credentials, and the project has been deployed in VAR World Wide Web HTML directory. So if you want to have the snapshots of code or anything, later you will be able to take the snapshots from the video itself. Okay. And if is there any question, you can ask me. Once I have got a query here. How to convert PEM file to PL file. PEM to PPK is a different concept to connect with PuTTY. So in order to do that, what you can do is, let me quickly share a video that how you can quickly convert PEM file into PPK file. Let me search convert PEM to PPK. Okay, on the chat section, I am sharing that how you can use PuTTY to connect to AWS using this video. You can quickly have a look. Okay, this will tell you. And all the other part is recorded in the current video, that how the model has been exported to PKL that I have recorded in the video. This is just to convert PEM file into PPK file for connecting to AWS. Okay, so I'll write that here. Converting PEM to PPK and connecting AWS server. Okay, so now you have the PEM file, you know what is the username, and from the video you'll get to know how you can quickly connect to AWS. as well as about the conversion of PPK. Sorry, exporting the model was very simple. Once you have got the algorithm model, let's say this was your algorithm, grid search KV, the kernel reg. I have quickly exported that using this model, export model, using pickle. You have to give any name. You can take any name. I have taken earthquake underscore model.pkl, and with this function pickle.dump, we can quickly export any model into that file. And once we have to use it for prediction over the web integration model, we just need to load the model and we have to predict using the loaded model. Okay, is that clear now? Any more queries? You can speak up also in case if you have any query. Okay, all clear? Okay, that's all. Thank you so much for watching.